We are recording. Cool. Okay, so today is chilling refactoring day. It's been a while since we did one of those. So my plan is let us look at each individual file and see what we can do to improve it. My first thing is I think we should make this a function.
Uh, Code put, then stack put 3 times for stack start, p register, and then setting the number of parameters to 0 because there are none at this
Uh,
point.
I think we should do halt program.
Well, not parameters, permanent registers. Yeah, this is a good candidate because like this is basically a big function composition, right?
Yes,
Well,
yes,
not that
yes,
big, but
yes.
you get what I mean.
Yeah, but this is very random. Like if you don't know exactly, I'd rather have a better name, which is like halt program, in which
Yeah,
you don't have to go into the details. You just
yeah,
skip through it. Okay, so we're
yeah.
gonna have a computer.
That's the names are comments philosophy, I guess.
Oh yeah. So lib compiler, not compiler, machine t, which reminds me, company mode is on. Let's disable that. We're also gonna need a compiler, which is lib compiler t. We also should say what we have done. L2 works.
Yeah, turns out the problem we were is that we were getting ahead of ourselves. L2 actually doesn't support nested calls. That's why it was broken.
Yep, yep, yep.
Also, there was a bug with register allocation. We did record that, right?
Bug with register location. I think so. No,
Oh,
actually, we
okay.
definitely did. We definitely did.
No need to go over that then.
Yeah, it's recorded. So boom. So this is the computer, and yeah, I kept it in there. And then we're gonna do all of these operations. And I also think we're gonna need these there. So let's put it in here. So then you can do all of those things, and this returns you a store. So that's actually exactly the return of this. And you also need the initial store of the freaking course. Um, that's a little bit annoying because I need to pass 3 arguments, and I don't really like that. I don't really like that.
Uh,
Can't we just do a similar thing here? Uh, like before all of this, we do a, I don't know, compile the machine or something, and then we can say stuff like boom, compiled, and then here instead of sending the initial, we're gonna send the full computer, which means that we can in fact also say e register and store and everything else, and then we can say hey man, boom, and we actually don't need the computer anymore, and that should be it. Of course, this is also incorrect because I need to say lib machine cell t. I really wanted to make this a type alias, man, but I don't know how to do that.
A type alias.
Yeah, like can we just do? I don't know if that's the way. Can I just do
Yeah, type,
store?
then the name, then equals, then the
Yeah,
type
but I think
definition.
I tried this before and it didn't work. I don't remember why. So the problem is syntax error. Oh, you need a module. You need a module.
Oh, wait, doesn't Magetta keep complaining that in OCaml files are modules?
Ah, that's one problem. Yes.
But main is not a module.
Oh yeah, main is not a module. As far as I
Why?
know. Maybe I'm incorrect. Maybe I'm wrong. Here's another problem. This is a type alias and this works. Why doesn't this one?
Oh, you need the type after the colon, don't you? Or wait.
I don't think that's the problem. The problem here is saying syntax error.
Unbound module store.
Yep. And but we know that this works if I actually do it like this. It works. Um,
That's very bizarre.
and that's very bizarre. Very, very bizarre. Um, okay, so let's see. So you have the initial computer, uh, in which you pass the store in it to the compile function. It does some stuff. You print the first 30 bytes of the computer memory. Then you update the store. Yeah, I would like us to try to compose these things, like all of these operations. Well, this one will definitely be the halt program, but I would like for us to try to compose all of these lets in a single let using pipes or something.
Welcome to concatenative programming, Lemos. Well, not quite, but I think you have the spirit.
Yeah, it's definitely not quite, but okay. Um, so how to do that?
You know what's the sad part?
What?
The thing that prevents that from being easy is the fact that we have all of these local names everywhere.
That's not what makes it hard.
If we didn't have those local names, this would be concatenative already, and so actually it would be just a matter of cutting and pasting.
But that's not the reason. It's hard. The reason is because this returns two things. That's what makes it inconvenient. Well, that's not really true because this is a tuple. So this actually returns one thing.
Which contains two others, yes.
Mm, well, let's try a naive attempt first. I know that when we are done, we're gonna have what? We're gonna have a compiler. And I also want to say that we're gonna have a computer. I want to say that. We're gonna start with an empty one. So let's put it in here. So the empty one is actually this. So there we go. We start with that. Then we call this function. Um, we call this function. Yes. But that's not gonna be enough. We're gonna need a lambda. So yeah, let's do it ugly first, then we make it pretty after. So fun. This is gonna be the initial computer, and I actually don't remember the syntax for lambdas. I think it is this, but you never know. You grab the initial computer. That's going to return you the compiler in the store. Compiler in the store. Uh, so let's say that compiler store. Yeah, I want a function that grabs man. But there's probably no function in OCaml that does what I want.
What do you want?
I want a function that allows me to pick a tuple and apply basically an fmap for tuples in Haskell. Allows me to fmap the second member of the tuple.
Uh, well, you can write that.
Well, I always can write that.
I think the reason that, well, assuming that function doesn't exist because it probably doesn't, I think the reason that's not a thing is because usually you would just destructure the tuple, right?
I have another question though.
Okay.
What about getting? Oh, but getting rid of the tuples at this stage is kind of annoying because they are kind of everywhere. How to use core tuple true as a core map key?
Uh,
Tuples, 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 and tuples. That's it? That's all we have about tuples. Damn. Let's actually make these auxiliary functions here, at least for now. Map fst, which is gonna grab a tuple, and yes, it's gonna grab a tuple. So there is a1, a2, and f. Uh, Ooh, you know what would be cool? What if you call it map and we say that you actually provide two functions? Like this. How about that?
uh, yeah, that's the basic. Congratulations, Lemo. You just wrote bimap.
Mm-hmm, mm-hmm. Let's actually piece the OCaml people off. Let's actually put by map here. There. Always a pleasure. Always a pleasure. Okay, cool. So in that case, that means that we can just do another pipe. We know that this function returns two things. So we're gonna do by map, which by the way, I need to reverse to tail call this thing. But that's the thing though. How do you do identity in OCaml? Identity OCaml. Is there? Oh, I think there is. You call that fun.id, I think. Uh, okay, so fun ID. Uh, then we need an update record function. OCaml. So how do you do that as a function? Because well, OCaml kind of dislikes functions. Well, constructors or record related stuff as functions. Record related stuff.
You know, that's that's the problem when your record labels are not first class. It's hard to have like a generic way to access a field of a record.
Yeah, but no, we're not trying to access one. We're trying to mm, use a lambda to do that without having to without having to write the lambda explicitly. Like even C++ allows us to do that. So there should be a way. There should be a way that allows us to do that. You see, this is the problem. This is in order to do this type of shiz, you need to have the a label for it, and that's what I'm trying to avoid.
Hmm.
Camel. First class fields. Consider the following function for extracting the usernames from a list. How? Here we wrote a small function. Exactly. How do you do the opposite of that? To access the user field. This kind of accessor function is a common enough pattern that it would be convenient to generate it automatically. The ppx fields conv syntax extension that ships with core does just that. The deriving fields notation at the end of the declaration of a record type will cause the extension to be applied to a given type
Oh,
declaration.
but this is from Jane Street, from core, right? We're
Yeah,
not
no,
using that.
we are not using that. But let's see if, well, this is just accessors. We don't want that. Let's see how far the extension goes. We can define logo as follows. So then you do the thing, right? And then there's a module. Oh fuck, you have to do this? You gotta be fucking kidding me. Is this not automatically being able to generate? That's kinda meh. This will generate a
Uh,
lot of output because fields_lib generate a large collection of helper functions for working with record fields. We only we only discuss a few of these, but you can learn about the in the remainder. One of the functions we obtain is logon user, which we can use to extract the field. Okay, this is it actually.
hmm.
Yeah, but we again, even if we would go through, even if we wanted to go through this hassle here of like, we're gonna have to make a module instead of just deriving the shiz, and add another field modules on the thing. We don't want to do any of that. We don't want to be doing any of that. Um, update the record field OCaml function. Yeah, my disappointment is growing. Function to update record field OCaml. Yeah, that doesn't change the. Is this in OCaml by any chance? Oh yeah. Uh, yeah, man. Why OCaml? Why you do this to me? Why do you do this to me? Cool. Well, let's make a function. Update store.
If you think about it, most of what people do when doing functional programming is making functions.
Yeah, no, I don't have problem writing the functions myself. My problem is that I have some expectations, let's say like that, and the fact that the language is not fulfilling my expectations is kind of annoying.
That's fair.
And I don't really understand. Like, and look at what makes it like. This is also would be better if it was partially applied, but as far as I remember, you cannot do that as well. Am I wrong?
Partially applied. You mean if the function was curried?
Yeah.
Ah,
Like, look at this type signature. What I want to do, I want to partially apply this shit and let the by map fulfill the rest. That's exactly what I want.
I mean, the way this is written, that should work, I think, because this is like you're not putting the arguments in a tuple, so they should be curried.
Look at this shit, man. Anyway. Okay, so what you're saying is that I should be able to do. This should be doable.
Yeah.
Okay. You know what would be even more cool? But this would require some syntax stuff. To like, I think Elixir does that. That I would put like an underscore here and here, and then I would be able to remove the lambda. That would be even more cool. What happens if I search remove lambdas OCaml? Deleting variables. What exactly do you mean by deleting variables? This is valid? Well, I guess that makes sense. And I'm not talking about doing that. Optimizing with lambda.
Really? Do you really prefer nested destructuring over a thread first, Mars? Ah, okay, I guess.
Well, we don't need the parentheses. Okay, that's cool. Thank you very much. Wait, what was the complaint?
Like, the PR that Mars is reviewing, he just asked if I could use a nested destructuring instead of binding followed by another binding with a thread first.
I see.
I mean, I guess I can do that. I just.
But I don't think the debate is about being able to do. We're probably able to do all of it. No, I don't think nobody's questioning your capacity, Marin.
The problem is that this will make the line very long.
Oh yeah, but that's because you use half of your monitor. Am I wrong?
That is technically correct, but also it's annoying when the line is very long and you have to move your eyes a lot to read the end of the line.
Yeah, I can understand that. Okay, let's continue here though. So after you do all of these things, including this, right? So what are you gonna have? You're actually gonna have still a tuple with the compiler on one hand and the computer on the other, What do we want to do next? We're not gonna have any of these, so this is gone. Bye. I'm gonna comment this. Oops, that's not what I wanted to do. We don't need these anymore because I'm already doing that with the update store. So bye. And then we're gonna call halt program now. So halt program. Okay, there is a better solution, in fact, which is cool, which is to make this a tuple. Boom, 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 boom. Not that. Boom, 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 and there we go. Which now just pipes into hot program. And that should give us, oh, this will now return this. This will now return this. What this will return, should return, is let store equals in record. This needs to return the compiler first, so compiler, then computer with store, and then the type signature. The type signature needs to change to this. I need another label for the computer. So as computer. Awesome. And I don't see the problem. What is the problem? Oh, I actually see the problem. I actually do see the problem. First is that this is in reverse, so the compiler needs to go first. So
Does this not work?
that, and this is also in reverse. And boom, boom, and then we do it like that. Awesome. And then how to program. And then all of this can disappear. Boom. Uh, it's way better now, which is cool. The stacked machine. Why do we need to do it? We don't have a store anymore, so this should just be computer with. Um, and I'm actually gonna rename. Oops, to computer. And that's it. Oops. What do you think, Marinho?
Let's see.
And I also think we don't need this redirection.
Initialize, then we take the initial computer and we compile. Then we update the store. Then we add the safety halt program at the end.
Yeah.
Uh, yeah, this is much nicer. This is much nicer.
Yeah, the details are all removed from the main thread. And then you pick the entry point from the compiler. If there is an entry point, you update the P register of the computer using the thing, which I'm actually gonna inline because why not? So boom, and then we can just say boom, and that's it.
I cannot believe I'm writing this function, Lemos.
Let's see if it compiles. Dune exec Karuta.
This is so silly.
Wait. It didn't print
Okay.
anything. Um, does that mean that I don't recall? I think I removed all the prints, so maybe that's why. But just to confirm, well, it's not a lazy language, so it should not be able to detect what I'm doing. So this, um,
Detect what?
then this, and then what is the type of this? Something, yeah, but I just want to do it like this. So can I just say print end line
Ah, this is
something
very sad. I wonder if I can.
something. Okay, so it is working. So let's revert, and that's it. Let's also FMT. Look how nicer it is now. This is it. This is what we do. So the first thing that we do is initialize a computer, then we compile, we update the store of the computer with that. We add the halting. That gives us a compiler and a computer. Then we check the compiler stuff entry point to see if the stuff is there is an entry point. If there is, we just say uh, eval eval. Okay, so in the auxiliary functions, do you see any potential improvements, Marin? Because I'm gonna commit this already.
Halt program. We have a bimap. We have update store.
Yeah, this
Halt.
function is such a joke, but okay.
Uh, Not really. No.
Cool.
It's very sad that I have to do what I'm doing. Okay, this doesn't work. The fact that closure strings need to be Java strings is very sad.
Well, JVM.
Can I conjunct to a string? I don't think I can.
Yeah, I don't think we can.
Yeah, I can't. Why not? Conjunct is
Tururu.
a protocol.
Tururu. Let's do a commit. So there we go.
Uh, okay.
Refactor main module, well, main file. There we go. Okay, so what's file is gonna be our next victim of improving, allegedly. I don't remember having anything to improve on the store. I think we did this pretty okay first time. There is some boilerplate, and there is a to-do here. Add top of trails arguments to be checked. Oh, okay, this is because we are just checking if um, you are not exceeding the, like, how can I say this? You're not exceeding one of the boundaries, not the other one.
Oh, this works actually. Man, this is gonna be so cursed.
Well, I'm not surprised. Oh, there's also what you wanted, right? Which is to make the declarations in the query outside of this type T and a separate type. Yeah, we can do that. Well, what do you think? Should we do? No, I'm not gonna do that right now. Today's supposed to be chilling, and that's gonna be a lot of work. So, registrar allocator. This one I remember having a lot of stuff to improve. Uh,
You know what I'm doing, Lemos? I'm writing a function that takes a UUID and changes the first digit.
that's very cursed.
Yes.
That's very, very cursed. Okay, so allocate. Can we improve allocate? Uh, we have these three arguments, then we do a match, and we have some special returns. Yeah, I think this is okay. Next up, allocate loop. So this is, well, returning another lambda. Oh, we did it like this because we wanted to have the full type signature like in Haskell. Okay. We should probably make a convention instead of just doing whatever, but that's okay. Then we check the front, then we do some stuff, and then there's some fail widths here, which is fine. Then we have allocate functor, which is fine. We have allocate variable, allocate variable. This is fine as well. Variables of term. Yep, this is very fine. Allocate declaration. So we first do this pattern matching, which is okay. Yeah, this is where the shit hits the fan.
Okay, this is so cursed, but it works.
And you're happy about it. That's the thing, you're happy about it. Uh, happy about it. Okay, so what do we want to do here? We want to grab this for sure. Grab that, put it in here, pipe to this, then pipe it again to this, and then pipe it to this. I think. I think that's kind of where we're at. Yep, that's it. So then you have to read bottom up. Jesus, okay, this one is even worse. So you do this, then what you want? You want to pipe into this function, then into this one, and then finally into that one. Boom. And then, oops, there we go. So there it is. Then we have some other pipes, which is also cool. Um, then we create a special thing. Wait, what the heck is going on here? We create something called terms, and this is a concatenation. This is a concatenation.
Okay, this works. Now this should work. Yeah, this can all go away. This can go away. This can go away.
Okay, let's make terms prime. So I'm gonna need this open as well. And what we're gonna do? We're gonna grab. Yeah, we're gonna grab the body. Then. Yeah. Then we're gonna apply this to the body. So boom. Then we do ft of list, and then
Okay, Lemos.
we're gonna
Oh,
be
not Lemos.
appending this as well, and probably gonna need some parentheses. Okay, that was not what I wanted. Probably gonna need that. Yeah, Manin, can you look at here? Can you look at this code?
Uh, okay, what's going on here?
Is terms prime equals to terms?
Is it equal to terms? Uh, let's see. We have elements plus Wait. We have the body. We're doing a concat map. Then we're piping that to ft of list. And then we're doing ft append, which is plus plus down there. Uh, yeah, it should be.
Okay, but is it worth the swap? Do you think?
Is it worth the swap?
Yeah, because this is the case in which we are doing only one of these, which is usually more reasonable. Usually.
Uh, I mean, honestly, this is such a small example that I don't think it matters that much.
What do you mean? In the sense that it doesn't matter which way we go?
Yeah, because this section of code that you're rewriting is so small. Like, I don't really see a big difference in readability between them. Actually, to be honest, I think I prefer the old one. Oddly
Mm,
enough.
which has an operator. Because one of the advantages of terms prime is that yeah, can also delete the plus plus definition.
I mean, you can delete the plus plus definition and do ft append and do parentheses on the ft of list. We just didn't do that because we thought it would be neater this way.
No, no, no. That was not because it would be neater. The reason was because
Oh, actually, we were doing plus plus more times before as well, right?
not only that, but I think that like the way that we are explaining to ourselves, because these plus plus, which one is on the left and which one is on the right matters. And I think we did it like this because doing it like this makes it less obvious which one is going to be the first. Because well, this line is going to be quite long if we do it like this. So we decided to do the plus plus to make it obvious that the elements comes first and then this concat map goes after.
I mean, with ft append, the value on the left will be on the left at the end, right?
Well, yes, but again, which one do you prefer? You said you prefer the non-prime one, right?
Yeah, I think that I prefer the plus plus version. Oh, actually, I remember now. The reason we did the plus plus is because there's no like, you know how in Haskell you can take a function and enclose it in backticks and it becomes an operator?
Yes,
We can't do that in OCaml.
yes. Well, but we're gonna continue going with the original way anyway. So let me undo this version. Then we have allocate query, which is fine. It's fine. It's fine. Yeah, but what about what I said before? Do you think we should make a convention about using this way or using this way?
Uh, oh, about whether we put the type signature.
Yeah, like this, and then have to make a lambda immediately after, or we do it like this.
Or we do it like this. I don't know, maybe I'm too used to looking at Haskell code, which is odd because I don't look at Haskell very often, but I actually prefer the type all in one place, and then we do a lambda.
Well, I'm also fine with that. Uh, I'm not gonna do that now though, because it's gonna be a hell pain in the very boring. Very boring. See, refactoring. I'd rather just do exec Karuta. It works. Do fmt. It also works. And then we just do a commit. So there it is. Refactor register allocator. Okay, which one is next? Parse. Yeah. Actually, believe it or not, this one can also be improved. Just by doing boom, 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 boom. Doing fmt. Doing exec Karuta. It works. This one was very easy. Effect parser. Nice. Machine. So do you have anything that horrendous going on here? Well, actually, we did have that. Uh, we can always get these comments later. Uh, okay. Doing fmt. It works. Machine module. Next up, evaluator. Very interesting. Okay, so this is where we did some of the lack of pipes, essentially. Yeah, we have a lot to go through this one. Let's actually go to the compiler first because it's smaller. So let's see. So allocate registers. We do a pattern match if it's a variable or function. Yeah, this is another to do that we can address. I'm not going to do that now. And if it's a declaration or a query, we just call this thing. The compile function, which is a recursive function. We do a pattern match, unreachable compile. Then if it's a declaration, we do some stuff, such as grabbing the functor table, grabbing an allocator, and using those two in the code generation. The code generation. Mm-hmm.
Lemos, look
Yes.
at this cursed thing and tell me what you think of it.
I have a question. Do we only need the functor table down there?
Functor table down there.
Wait. Where is the first functor table coming from?
It comes from the compiler, no?
Oh, here. Okay. Yeah, but is this
Like,
the functor table only used down there? That's what, yeah, exactly. So what I think we can do is actually to grab this and put it in here, and then we can remove. Um, we can actually do it like this. In fact, boom. There we go. Very cool.
I posted a very cursed thing in the chat, Lemos.
Uh, yes, it's just as cursed as I imagine. Yes, very cursed.
It bothers me that, like, actually, let me check something real quick. I'll have to look at Java documentation for this.
Java documentation. How cool. How cool. Yeah, okay, this can be a gigantic pipe as well, actually. Okay, let's actually do that. So everything is going to start with a form. Everything's going to start with a form. Then what we're gonna do, we're gonna allocate the registers. This will give us an allocator, which we can use it down there to do our stuff. So I can
Oh, I can actually,
go.
right, I can actually do a string replace. That would be easier.
There. Well, that's true. You can do what you said. It actually makes more sense, given the how cursed that is. So then that will happen. Then what we're gonna do? We're actually gonna have another lambda here with the well. Oof, 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 oof. That's a little annoying, but that's okay. Then we can do it sort of like this, sort of. These can go on the top, and then we put parentheses here and do it like this. And this should actually, oops, this should actually just be just fine. This should actually be just fine. Look at how annoying this is. Look at here. The P register here needs to be the original P register, but the P register here needs to be the one from the code generator.
Yes, it has to be.
That's that's hell of annoying. That is hell of annoying. Okay, what do you think about this version here? Uh, is it okay this way, or do you prefer the older way?
Let's see, we take the form, allocate registers, then we grab the allocator and generate passing a new code generator. Then we take the code generator in the store and we compile into the store. Passing the rest of the declarations as the next thing to compile. And we update the compiler by setting the P register and the functor table. Yeah, no, this actually looks pretty good.
Yeah, basically this pipe is removing the labels, the intermediary labels. Well, they are not really gone, they are now in the lambdas, essentially. But now this is more explicit, the pipeline. Like, it's very explicit that we first do this, then we do this, then we finally do this. That's what we do. That's what we do. Which is a very similar process to what we're supposed to do here. Okay, so form, we start with a form, then we allocate stuff to it, boom. Then there's a lambda, fun, allocator, boom. Uh, let's move this here. Then we're gonna do that. Then you grab it here, and this now is gone. And then we finally add extra parentheses. And now we just indent. And there we go.
Yeah, so I can actually just use a replace first instead of doing the whole turn it into a vector, then set the first item explicitly and then map back to a string and join.
Yeah, that's much better. That is in fact much better.
Mm,
Uh, I'm a little bothered that a lot of the code is still the same, right? So if you look at what we are doing for declarations and what we are doing for the queries, aside from the entry point pattern match, we are doing the entry point to in the recursive call. In the declaration there, we are not setting the entry point. In the queries, we are, but everything else is the same.
we can probably factor out the pipeline of allocate registers and then the allocator function. Oh, the function taking the allocator, I should say.
Yeah,
Although
yeah,
the
exactly.
allocator and the store are coming as from arguments, right?
Yes, they are coming
From
from above. And I think that removing these explicit pipeline would make it harder to read because right now it's pretty clear that we first allocate the registers, then we could do the code generation, then we do the recursive call.
uh, yeah, leave it as it is. If the same if the same thing repeats a third time, then we can talk about factoring them out. But with just two occurrences, trying to factor it out will make it harder to read, and we're not really gaining much.
Yeah, it still works. And if I FMT, it's not. Yep, if I FMT, this is how it looks like, which uh, it's polarizing, I would say. So the first two pipes they go together because the line is too short, and then it breaks because of the code generation, and then there's another pipe.
Uh, that's
Uh,
probably okay.
yeah, but I think it's much better to reverse this, like so, because then we can remove one pipe, given that we're not gaining much from using it again. Yeah, yeah. This is probably okay. Uh, this is probably okay.
Function composition is very nice.
Yes, it is, but man, I really dislike, and this is also a problem with Haskell because, like, what would be even more cool, even more, uh, is if this allocator was in tail call position.
You mean if it was the final parameter?
Yeah, because then I could get rid of the lambda. The problem is that this is a recursive function, and this is part of the state. So like it kind of needs to be in a triplet.
Uh, I mean,
Yeah, I think we leave it as it is. We leave it as it is. Let's do another commit. So this is refactor compiler module. Now we are getting to the big dogs, which is the code generation and the evaluator. Let's do the evaluator first. So what can be improved in here? What can be improved in here? I have a question. Are we doing how many with store? Quite a few. Quite a few.
Mm,
Do you see any improvements on the set register? Given that we cannot compose record updates.
set record. Where?
Oh, set yeah. I don't know, line 8 and 11, line 17 and 20.
I don't think it's worthwhile because this is a very small chunk of code. Although, hmm, I don't know. Do we call this int map add elsewhere?
Int map add elsewhere. I don't think so. I don't remember actually, but probably not.
Oh, not oh, not really the int map adds. The point is like, do we add stuff to the registers in any other place than just this function?
No.
If we don't, then like
Int
I
map
don't really see the point of trying to refactor this.
let uh, record update with pipes OCaml. Functional update. Well, yeah, I think we're gonna go as it is. Um, cool. Um, let us continue. So the get register. Do you see any potential improvements in get register? I don't. Personally, I don't. Marinho?
One moment, I'm replying to Mars.
Sure.
Improvements. Find, then on the other branch, we get the thing. If it's an address, we do a range check and we do a get. Yeah, no, I think this is pretty much as good as it will get.
Okay.
I mean,
You mean?
the only thing we could try to improve is removing the fail is, but that looks pretty hard.
Yeah. Question. Question for you. What about the? Oh, we are kind of already doing that. The store is already on the last argument thing. Sure. 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 Let's do it like this then. So h register. We're gonna do a store heap put structure. Uh, well,
Mm,
actually, this is a store. Then we're gonna grab this, put it in here, and then we're gonna do this thing. This goes away, yeah, because the order does matter. I need to be very careful. I need to be very careful. Um, damn. Damn, 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 damn. Damn, damn, damn. I have a question.
Okay, what's the question?
Do you see line 45 and line 50? Do we need to
40,
do 45 before 50 necessarily?
before 50 necessarily. Uh,
I don't think
this is
so.
the evaluator, right?
Yeah.
Structure cell, then we create the functor. Then line 45 is we update the store first. Line 50 is we update the register.
The computer with the setting the register. Thoughts?
You can swap them, that shouldn't break anything, but you have to be mindful about not swapping line 51 because that has to be at the end. Well, I guess not because, well, yes, because otherwise we're going to mess things up because we're using the same variable name.
The set register uses the H register? No, it doesn't. So we don't need to care about that as well. Because here's what I want to do. Here's
But
my
we're using the
evil
H
plan.
register on line 48, which is part of the thing on line 45.
Yes, but I want to put these three things in the pipe.
Okay.
So here's what I want to do. Here's what I want to do. Actually, there's another problem going on. Does it matter? Are we using the store in the set register? We are, actually. We are in fact using the store in the set register. So this matters. I need to have to do this. Like I cannot just pick the store and update this computer with it and then call the set register. I need to be using the old store. Right.
The thing about the set register though is that they are not actually, it's not actually looking at, because line 45, well, 47 and 48 really, we're updating the heap, right?
Mm-hmm.
But set register is only going to look at the stack, not the heap. So it's actually safe to swap those.
Okay, that's good. So here's my plan. We do fun store. This is gonna give us a store. Uh, and then we grab this. Uh, okay. So here's the thing, though. This is very risky what I'm about to do. You see this computer here?
Yeah.
Can I update its H register and its store and then call set register?
And then call the set register.
Yeah, because set register doesn't use the H register. It does use the store, but it does in a different section, so it doesn't matter. So theoretically speaking, it doesn't matter. But
Yeah, you
I'm
should be able to do that. You
yeah
should be
yeah
able to do the set register later after the age register.
exactly. But I'm asking if like it's gonna look really neat, but I'm questioning if you're gonna trade off readability.
Uh,
Because look what I'm gonna do. I'm gonna do this.
and then set register.
And that's it actually. All of this gone. And
That's actually way better.
yeah, no, it's gonna look really neat. But in terms of are we sacrificing readability to achieve it?
Hmm. I don't think we are actually.
Okay, so all of this, boom, and all of this, boom. That's a new put structure. Let's see if it doesn't blow up, and it doesn't. Awesome. Okay, some spacing was added here, but this looks pretty neat. Now, this looks pretty neat.
Hmm.
Next up, so set variable. What can we do here? What can we do? The same thing, actually. The same exact thing. Awesome. So let's do it. So store is gonna start with store. Then it's gonna go to this. Oops. Then it's gonna go to this sort of stuff. So boom. But this is actually +1. And then we do the set register, and then we are done. So boom, 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 and boom. Done. Done. Next up, set value. So what are we doing? Yeah, we're doing the exactly the same shit. Okay. Uh, yeah, this is the same as before.
Hmm.
So store heap put on it. Boom. Then we do this thing, and we actually don't have an extra set register operation for that, so this is also gone, which is kind of neat. Kinda neat. Deref. Yeah, this is as close as gonna get. Bind is also very okay. Okay, now we are getting to the big boys. So get structure. What are we doing? We do a pattern match, get the address, then we check if the address is in fact a reference. Then we create a structure, create a functor. This is definitely going to be reverted. So um, we do this thing first. Then we do this thing second. And then we do this thing finally. So that. Um, yeah. Yeah, look at this function.
I'm looking at this function.
Get structure. Do you see any improvements that we can make here? I just added the pipes. Before it was using the at.
Heap put bind in computer. Yeah, no, I think this is. I don't really see any easy way to improve this.
Yeah, to me this is very close to what we're gonna get. And I just noticed the order of the puts doesn't matter. That's a little dangerous. Because in this case it doesn't matter, but I don't know about the others. It shouldn't matter as well, but unify variable. Yeah, and there is the unify mutability city that I'm not really in the mood of fixing that problem here. So let's see. So you grab the store, you do this, then you pass that to that. Hmm, is this worth it though? Yes, it is, actually. In fact, it is. So we're gonna do store. Then we need to copy one of our previous fixes of this nature. But this time is S register. It's freaking S register. And then we do the set register. Actually, we don't even need the store in this particular case. It's actually this is a pretty good one to ask you what you think about it. So look here. What do you see as improvement here? Because I'm not certain putting pipes here will improve anything.
Let's see, we get the value. We set the register with the value in the computer, and then we bump the S register. I guess you can inline the S register bump in line 116.
That's true. I can definitely do that. So, boom. What else?
Uh, hmm.
Only these 3 lines, by the way. Not the other ones.
Hmm.
Like what bothers me is because you have computer here and computer here.
You can actually get rid of that second let and put the register after the in as the argument to the set register, because setting the register shouldn't touch the S register at all.
That's true. So let's actually do that, and then this returns this. Two lines. What else?
Uh,
I don't know if inlining the value is. I don't think that's a good idea.
we can do that if we use a pipe. Like,
I don't see.
if you put the computer with first, then pipe that into the set register, you can inline the value at the end.
Oh, you mean basically putting this in the beginning of a pipe, then set register value, and then this in this.
Yeah, set register, and then that directly at the end.
I don't know if that's gonna be readable though. A little bit skeptical.
I'm not sure I like it either, to be honest, but it's a possibility.
Yeah, no, possibility I agree, but I don't know if we actually should do that. To be completely honest with you.
Okay, let me just give me a moment. I need to mark what I already did from the PR comments here.
So this, and then this, which actually is gonna terminate on this. Yep, that's exactly what are we talking about. Yeah, we did some changes. Let's see if it still works.
I
It still
answered
works.
this. Okay.
Okay, but well, you need to make a decision right now. What's your opinion? Keep these two lines as it is, or converting another two lines using a pipe and inlining the value.
Just keep it as it is.
Okay. Okay. I'm not gonna touch. Well, that's a lie. I will touch this part of the
This is
process,
done. This is done.
which is to say,
I have too many tabs open.
classic. This, I'm definitely gonna
Go
put it
away. I
in
don't need
here.
this. I don't need this. I think I have this open elsewhere.
This can go away. And then I can just say that with that. Awesome. I'm not gonna touch this part because well, this is gonna be a recursive function in the
Mm,
future. Does it work? Yes, still works. A little bit of formatting. Let's continue. So unify value. We have a pattern matching. I'm gonna do that. Yeah, and this is the classic. So store uh, that, and then that, and then we need to go up here. Copy, not that. We need to go here. Copy that.
okay. This is done.
S register. Also the store, and then this is done. Cool. I guess the formatting will disagree about the indentation, but that's okay. Put variable. Put variable. Ooh. Okay, this one is already using pipes, which is good. So store. I'm just gonna basically combine them. This. Boom. Which is gonna be then piped through this and then that. So then boom, boom, which then is gonna be piped into the fun. So where is the fun? This fun. Okay, there we go. This is actually a computer, and we need to update the. We can do H register updates before doing set registers, right?
Uh, yeah, we should be able to, yes.
So this can happen here, which means that this is the store, and then all of this is gone. Boom. Are you're sure, right?
Yes.
Okay. So that's it. Just a bunch of pipes. Yeah, this is definitely worth it. Let's see if it still works. It does. FMT. This is very neat. Then you have the put.
Are you actually running the program in main.ml though?
Yes, we are running the program. I don't know if it's the best program, but you're running this there.
Oh, right, we got rid of all those prints that we were using
Yes,
to debug stuff.
exactly.
Okay.
Well, I didn't get rid of them. I just comment them out. I just commented them out. Another two-line dilemma. I think we keep it as it is. Your opinion.
Uh, yeah, just keep it as it is.
Okay. The same for the get variable. Get value is just unify. Let's see the allocate. So the allocate grabs some registers and it does some stuff with them. And then it returns the updated. That's a little sus.
Give me a moment.
Ah, I see. Maybe this is the reason. No, that's not the reason. Yeah, this is just I think I have an idea. Yeah, let me know when you are looking at the screen. How much time you're at? Wow, 1 hour and a half already.
Okay, I'm looking at the screen. What's up?
Look, do you agree I can do this? Boom, 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 and then that's it. Did you follow all of that?
Uh, do that one more time, please.
Yes. Okay, so before it was like this. Okay?
Okay, computer with the P register and E register.
Which are coming from line 204,
Yes,
which are basically 207.
yes. Oh, I see what you did. Yeah, that should work, I think.
Yeah, so this, this, and this. And that's it. That's actually it. Yeah, I think this is the shortest, the best that we can make. Oof. Okay, so allocate function. So there's the new e, and then there's a bunch of store stuff. This returns the store. Yes. The store actually starts here. So let me actually invert these ats to a bunch of pipes. So we first do the new e, then we do this, and then finally we do this, and then boom boom. Okay. Then we do.
Bonus, the plus are now in order. The pluses.
Yeah, but this doesn't really matter because we are using immutable data structures, and the indexes are different. So we could revert, well, put in whatever order that, and I think it would work.
Yeah, but this is neater.
That's fair. What about these though? What about those? I'm kind
Uh,
of tempted, not gonna lie. Yeah, I think I'm gonna do it. So here's the thing. So what we're gonna do, we're gonna say fun store equals, and then we're gonna grab this line, put it in here, but we're gonna do the updates. Oops,
+1. And E
and
register is new E.
new e, and then all of this. Uh, well, not really can go away because I want to keep this comment alive, and then this can go away, and then these can also go away, and then these pipes just do it like this, and
Yeah,
if
just
everything I did was correctly, fmt will wait. It didn't change this. Save
it just
anyway? No.
it did actually. Just changed the indentation slightly. Go look at the terminal.
Yeah, but I need to revert my buffer. Yes.
Oh,
Uh, okay, now it's correct. Look at the terminal. No, it didn't do what I wanted though. Now it did. Oh, it didn't. Okay, let's say that
the instruction
the
size is 1.
yeah, boom boom is one. And then if I say this, okay, the instruction size is one. Yeah, this looks neat. I I think.
Technically, you can replace the comment by using a let, saying instruction size equals 1 in, and then do plus the instruction size instead of plus 1.
That's not a bad idea, but I have a even better one. Why not make that global? Because then we can use it in here.
Yeah, that's better, probably.
So let instruction size equals 1. Then we can get rid of that, and then we can say instruction size. And I'm gonna already immediately put this in here, which removes the comment. And if we do fmt, yeah, now it did what I wanted, which is to break this down, because now the line is long enough. Let's see. So what is supposed to be happening here? Um, well, this is actually just a bunch of equals. Um, grab that, and then we just boom, and that's it. Proceed is just that, which is okay. And now the big chungus. Evolve step. Uh, why? There is something a little weird. Yeah.
Something a little weird.
Oh, okay. We didn't do, yeah, because in the majority of the cases we're doing p register plus one, and I was asking myself why we didn't do that externally, like after this pattern match we just do for everyone. But the reason is because of these three guys.
Yeah, they don't actually do that.
Yeah.
I mean, halt could, but proceed and call predicates can't.
Yeah, that's okay. Okay, what about the evolve function? Can we improve this somehow?
Uh,
That's tough.
I mean, we could inline the eval step and get rid of the boolean return value.
Yeah, but how are we gonna stop?
Oh, but then we would have to do a tail call inside of the eval step, which would have to be repeated everywhere.
Oh yeah. I kind of want to use bimap again, but the problem is that I need the. Actually, we can't use bimap because we need a computer that comes with the stop in the next evolve. So it's more like a fold and less of a like the tuple. The tuple is here just for convenience. That we actually need the data like in a very pipeline manner.
I mean, we could use a. Hmm. Actually, we cannot use a fold, indeed.
Yeah. Um, well, we can use a fold, but the gains are negligible.
Like, unless we get rid of the eval step and replace all those booleans with like tail calls, except the true one in the halt, then I don't really see a way to improve this.
Um, I'm thinking.
3.4 seconds, Lemos.
What is that reference for?
There's a parody of it's a parody of Metal Gear where the guy did a voiceover that sounds like it could have actually be in the original game, where the villain is monologuing about Big Chungus, and he mentions that Big Chungus only existed for 3.4 seconds, but he's more popular than Bugs Bunny, despite being Bugs Bunny himself.
I see. There is a way. I found a way. The way is to put the stop inside the computer. Thoughts?
Uh, I mean, I guess.
Because then we can just use one pipe and done. Well, we're gonna have to check the stop somewhere else, but I don't know if it's worth it because the computer is only hardware stuff, and we're gonna put a boolean that is just for the evaluation step. It's kind of like mixing concerns in a sense.
I mean, technically the hardware needs to know when to stop, but yeah, I don't really like that, to be honest. I'd rather keep it as it is.
Okay, so let's see if it works, and it does, and let's format it. And we did the evaluator. Uh, okay, so please take a look because some of the changes may be sensible. So, are you looking?
I'm looking.
Yeah, so let's go through the diff here. So, this is what I want change. So, okay, so far. This one as well, right?
All right.
Cool. Yeah. Then, yeah, these are the changes that are the most important. So, we do the store stuff. Well, what we were doing before. We do a heap put and another heap put using the h register plus 1. What we were doing, the heap put, h register plus 1. Then we update the computer with the store and the h register plus true, which we were doing at the end of the old way. And then we do the set register. Is that okay?
Yeah, it should be. Set register doesn't care about the age register at all.
Okay, then we do the same kind of behavior here, but with h register plus 1. So, okay, so far.
Yeah,
Then we
that seems
do
okay.
then we do this, which is the same, h register plus 1. Then we do this, which is store put h register, then h register plus 1, then the bind, which is the same but using pipes, which is more geometric. Then here we we do set register with the s register, not the h, the s register plus 1. Follow me so far?
Yeah, that's just an inlining, right?
Yeah, then here we pick the store, do a heap put with the reference. We update the computer, updating the H register and the S register plus 1 on both, and then we do the set register. Is that okay?
Yeah, it should be. Again, the set register doesn't care about either the age or the S register.
Yeah. Then we have the unify, which picks the store, does a PDL push on the address of 1, then the address a true, and then updates the store and the fail.
Yeah, this is actually the same, but backwards because we are using pipes.
Yeah. Then we have this again, which grabs the store, does a put, then updates everything with plus ones on the H and the S. Next up, we do a store heap put with the reference, and then before we were doing two set register in a row and then updating the computer at the end, the computer that we're gonna return. Here
But no,
instead, we do
yeah, we're updating the
the
computer first and then doing the set register. But again, it doesn't care about the age register, so this should be fine.
yeah, and the order is the same, A and then X. Good. Uh,
Um,
What?
Yeah, I think the A and X order could be swapped. Like the order doesn't actually matter, but let's keep it as it is.
Sure. Then we have this one, which again was doing the update of the computer at the end and using that P register and E register coming from here, otherwise it fails. So because it fails on the other branch, it doesn't really matter that like this is just unnecessary indirection. We just move the computer to inside the pattern match and remove those extra bindings.
Yeah, this is fine.
Then instruction size equals 1. What are we doing now? We are grabbing the store. Yeah, this one was one of the best refactorings because it's a single pipe now. We grab the store, we do an address with the E register, then with the CP register, then with the address N, and then update the computer changing the store, the P register to be plus the instruction size, and the E register to be the new E. Here, basically, it's a single computer update, changing the CP register to be P register plus instruction size, and the P registers to be the result of the find. That's it.
Yeah, yeah, that looks good.
Okay, so refactor evaluator module. Uh, and I think that we are on our last module, which is the biggest one, the
Code gen.
code gen. Yeah. But after we do this, we're gonna be able to merge L2 finally. So let us start. Let us start.
Okay,
Um,
I'll be right back. Give me a moment.
sure. Okay, so continue the
All
recording.
right.
Man, what about this one? This one is kind of interesting because we could inline all of this in here, but I don't know if it's
Uh,
worth it actually.
all of this where?
All of this we could inline it in here.
Uh, well, it's 2 lines. It's going to stay 2 lines after you reformat. I don't think it matters.
Yeah, that's true. Okay. Emit nested argument. Is there anything that you can improve on this function?
Oh, those are the ones that are. There might be a way to deduplicate those nested arguments functions, but honestly, I don't really see it right now. I would have to refer back to. Actually, I didn't publish the closure version of this thing, right? That I
No,
translated when I was debugging.
no. And I don't think you actually made the parallel enclosure of this part of the code. This is code generation. I
Uh,
think you did register allocation.
Alright, I only did register allocation. That's correct.
Yeah. So, can we improve anything in here?
I
It,
don't know. I'm not
yeah,
sure.
this
I would
this
have
is
to
the
look at it.
yeah, but this is the code that has the most amount of these patterns, such as you have a generator in a store, which are not in tail call, and then you get
That's
the new
not
ones.
that's not what tail call means, but okay.
No, I know that's not what it means, but if they were in what I'm calling tail call, I would be able to make this a single tail call pipe potentially. Because maybe I want to go through a bunch of functions, just this being the accumulator in the final argument position. This is what I'm calling tail call.
Uh,
I think it's worth trying though to like swap the positions of these two things. What do you think?
the position of these two things.
Yeah, put this here and just let it break, and then we see what happens.
Okay.
Okay, so now it's gonna break as fuck. So let's see. So this is now
Uh,
instruction goes here.
do we need to? Oh, okay.
Yeah. So probably this is gonna be useful. I don't know yet. Um, uh, so here the instruction will come first. So what are we doing here? Okay, okay. So here you don't see any potential improvements, right?
Uh, the register is this, the instruction is this. We add the instruction. Then we match a limb, which is an argument.
And then depending on what it is, we do different stuff with the generator.
If it's a variable or a functor.
Yep. I think this is it for this function. What do you say?
The register is going to where though?
Here.
Oh right, it's actually okay. Yeah, it's part of the instruction, I see.
I think that's it.
Yeah, that's about it. The only way to improve this would be to refactor the types so we don't mix top level stuff
Yeah,
with
but we're
term
gonna do.
level stuff.
Yeah, but that's a second degree of refactoring. That's not what we are here for today. If we have time, we can make it, but we have 14 minutes to get this done. Okay, so emit q nested argument. So what do we have in here? Yeah, this type of stuff is kind of annoying because this is basically the same as before, but because it's not a tuple of tuples, like this is not a tuple in which there's a tuple inside, this is actually a triplet, we need to deconstruct it in order to create the triplet.
Yeah, that's kind of sad.
Yeah, so, but I think that's it. I don't see how we can improve this function.
Uh,
The pattern matching is very different.
yeah, no, not really.
Yep. So next one, emit q argument. So we do a pattern matching there. Oh, this one we can improve. Immediately I already can see that this is a pipe. Which begs the question, what are you? So this is in a D, which I don't know why we called D. I'm gonna call this, I don't know, lm. And then what we're gonna do, we're gonna say lm this receives this there, and then that we're gonna pipe to this thing. Wait. Oh no, that's correct. That is correct indeed. So this now goes here, and all of this, oops, all of this can go away. Okay, that's nicer. Next up, emit argument. Okay, so the reason this is broken is because I need to swap these. You see any potential improvements?
Emit argument. We try to find a variable. We do different things depending on if we find it or not. We add an instruction and then we construct the triple. Yeah, I don't think that's gonna change.
Yep. I think also that. Okay, we are done with facts, now argument. So emit argument or inside the argument module. Any improvements that we can foresee? aside from swapping this. So we got the register. Ooh, we actually have some auxiliary constructors going on. This is called the variable, the value, and the catch-all. I don't think we can improve this. Do you?
Uh, yeah, not really.
Yeah. Yep. Yeah.
We could make a helper function that takes a generator and a store. Uh,
And
well,
puts
that
the
takes the
allocator in the
allocator
middle.
and then takes a pair of the generator and the store and constructs the triple. That would allow us to like,
Pipe some stuff.
yeah.
Sure. Let's actually do that. So let's go all the way up and let's make a function here. So the function will be called put allocator, maybe. I'm not good with names right now. So we're gonna have an allocator which has the type register allocator, probably T, and then we're gonna receive other things such as the generator and the store, and the type of this is the type of that is T cell T store T. And what we're gonna return? We're gonna return um, a triplet, which is T register allocator T and cell store oops T store T.
Can you believe that I wrote a unit test for a set? Like not a function, but an actual set.
Wait, but you're not supposed to do that. We're not there testing data structures.
But there is an invariant that that particular set needs to hold. It needs to be a subset of another set that's defined elsewhere.
Yeah, that's pretty cool then. Congrats. Okay, so now that we have this, let's go through the places in which we are doing that thingy, such as this one. This is a perfect place to start. So what we're gonna do? We're gonna grab the generator and the store. We're gonna pipe them into add, such as this, and then we're gonna put allocator, passing the allocator, and that should be it. And it is, in fact. I also think this is going to be a very common pattern, so I'm actually going to pick that. I don't think we can do it in here though, because we're doing a fold at the end. So let's not do that. What else? What else? What else? What else? Yeah, I think this is another place in which we can do the stuff. So grab this, put it in here, get rid of that, and then you can get rid of all of that. Awesome. Same thing, there's a fold there. Next up. Same thing. Boom, boom, that. Yeah, no, this is definitely okay. We also can do this in here. So generator store. Oops. Then add the instruction. And then finally put allocator, allocator. And there we go. Next up, uh, another fold, which means that we cannot use it. So I grab that. Mm-hmm. Well, in theory, we could make a lambda to put in the correct place in the fold. Do you think it's worth it?
Uh, emit query, fold left.
Yeah, these two lines can turn into do this, then fold, then pipe here, and then pipe into a lambda in which we put in. Actually, no, this, then this in the pipe, then put allocator, then we do a lambda with another pipe to put the triplet in here. Do you think it's worth it?
Uh,
This one is a little bit. Um, I would let keep it as it is.
yeah, just keep it. I don't think we're gaining enough to do that.
Okay. Let me save the stuff. Okay, so next up, um, instruction goes there. Can we improve this one? This is the allocate head, by the way. Can we improve it
Mm,
somehow? There is the head folder, which does some stuff. It does some stuff. I can already tell that it's better to actually do this.
yeah, get rid of the underscore register, please.
Wait.
Yeah, it's find element registers, but the way you move the code, it became find element registers underscore register.
Ah, okay. Oh, okay, that's why I did that, because we need it in here. There was a reason. Okay, never mind then. This instruction can be here, closer to the add instruction. What else?
Mm,
Yeah, I think this function, although not pretty, I don't think we can improve this that much.
I mean, yeah, no, just keep it.
Okay, allocate body. So we have inside that a bunch of inner functions that I could not decoupled before, which is allocate, or I didn't want to as well, maybe. Allocate clause, there's an allocate argument, which starts by, yeah, we do a pattern match, see if it's a variable. If it is, we get the raw register, the left register, then we find out the scope registers in the instruction, and then we create the new generator and store, and then pass those with the counter incrementing. Yeah, another one, not pretty. I can't see really an improvement here. Yeah, the code is pretty tight. Let's say like these, especially this part, it's not something that we can easily rewrite without changing important stuff.
Mm,
Do you see any way to improve this or?
I don't think I do actually.
Oh, this one I see. This one doesn't need the raw register because we're not using it down there. So this one we can actually put this find directly here and get rid of it. That's an improvement. Yeah, I don't see any other improvements. So let's keep going. This one we have an improvement. Okay, so generator store um, pipe add instruction without these, and then put our friend allocator in there. And the same thing applies here. So I'm actually gonna copy this and put it like so. Do you see any other improvements
Mm,
that we can potentially make? I see another one. This here. What else? What else? What else? What else? I think that's it for me. Ideas.
yeah, I think that's about it. I can't really see anything else. And I'm
Final.
still messing around with that review.
Okay, but final function. So let's try to finish this one. This is the last file, by the way. So we are getting pretty close to the goal of today. Um, ooh. Okay, this one I already see an improvement that we can make, which is great. Uh, more pipes. So generator store pipe that to add instruction. Get rid of that, which is then piped again into more this, and then yep, I can see more. So we're gonna make a fun with generator and the store, and we're gonna do this. So that this and store, and then finally put allocator boom boom, and that's a parenthesis right there. Okay, that's much better, right? Marinho?
Mm, let's see, generate. We build the triple by doing a fold left, emitting the query. Then we get the instruction for the call. We add the instruction, we add a halt. Then we set the variables to empty.
and then we just put the allocator. That's it. This is better, way better than what was before. Okay?
And then we do put the allocator. Do we actually need to return the generator here? We do, right?
Yeah, because this is a recursive function.
Right, right.
Functor time. So we do a register, we do the instruction, add instruction. Again, we cannot really do the pipes trick here. Then we do another fold. So another fold here. Uh, and then we finally update with the allocator as well.
We don't need to destructure the triple on line 304, by the way.
That is true. But then you're gonna, what name I'm gonna put here?
I don't know, triple maybe.
Yeah, but that's exactly the situation that I'm trying to avoid. But you're right, we don't need to like, I think it's only a readability gain. There is no, we could put whatever name here and get the same result.
Call
But
it gas.
oh man, I think I'm gonna regret, but I will do it just because it's funny.
We're passing gas around.
Yeah. And then we do this update here. Okay, final stretch declaration. We do same thing. So gas here. Uh, uh, gas here. And then the instruction. Actually, this can be improved. So generator store pipe. Get rid of you. And then
I think you're
finally,
gonna need parentheses there, actually. Oh no, you
uh,
don't, because that's a nullary instruction. I see.
done, and then done, and then that's it. That's it. That's actually it, believe it or not. So does it compile? That's the question. It does. And if you format it, okay. So wow, it shrank a little bit, which is kind of weird. I was not expecting to be less lines of code, but well. Okay, final checks before we finish today. Um, so we created a put allocator function and we reversed the order of the arguments of the add instruction in order to be able to pipe it more easily. Here, just doing the pipes, reversing. Here is a improvement. So instead of having result, we just do uh, ooh, this one can be improved even further.
This one.
Yeah, so Q nested this one. Yeah, it can it can actually be improved further because we can pick this and put it in here and make it this.
Yeah,
Even.
that's actually nicer.
Yeah, but is there a way to use put allocator? Because you see there we have the trip. Well, we are constructing the triplet for the first time. I think it's fine actually to do it by hand. There's no much gain in not in doing it otherwise. Okay, so this is now way better. Next up, the same pattern. So we do the add instruction with a change generator. with an instruction and then put the allocator. So that's exactly what you're doing here. Reversing, same things as before, but with the pipes. Same thing as before, but with the pipes, and put the allocator. Reversing, just change the location. Reversing, reverting I should say, reverting the order. This, yeah, change the order. This one, removed the raw register and put it in line. That's better. Reverse. This one, um, we do instruction. Oh, we move the instruction from here to here, and then we do the same trick as before. Cool. This one, deallocate, and then do the same trick as before. Oh, this one is a very nice one. So we pick that, we do the add instruction with the instructions that you just created, then we add halt, then we update the generator with the variables equal to empty, and we add the allocator at the end. Cool. Renaming, basically, renaming again, and changing the result to be to put proceed using the pipes instead of doing this thing, and put the allocator at the end. That's it. So let's check this in fact works. We can stage it and then code generator module.
Yeah, I think this is nice. This is much nicer.
That's it. I'm gonna finish the recording now.
Bye, future people.
Bye.